At this very moment, you are traversing space at almost 2 million miles per hour. Our planet rotates, the sun revolves around the Milky Way, and the entire galaxy journeys across the cosmos. Such immense movement means you cover thousands of miles every minute. Should this topic interest you, subscribe and join our quest to reveal the universe's signals and narratives etched among the stars. Each individual who has ever existed has done so beneath the radiance of one particular star. This star, our Sun, is situated approximately 26,000 light-years from the Milky Way's core, nestled within a smaller spiral arm known as the Orion Spur. From our vantage point, we gaze upon a stellar disk of such immense size that light requires a full 100,000 years to traverse it from edge to edge. The Milky Way, a barred spiral galaxy, presents as a slender vortex of stars and gas, forming luminous arms that arc away from a brilliant central bar. Seen from an aerial perspective, it would appear as a glowing pinwheel. Its spiral arms are delineated by youthful blue stars and brilliant gaseous nebulae. Within its nucleus resides a supermassive black hole, Sagittarius A, possessing roughly 4 million times the mass of our Sun. This unseen powerhouse exerts such formidable gravitational pull that absolutely nothing, not even light, can break free. Surrounding it, gas and dust revolve within an accretion disk, accelerating to velocities approaching that of light, reaching temperatures of millions of degrees, and emitting powerful bursts of X-rays and radio waves. A handful of stars, ensnared by its gravitational hold, circle this dark entity with incredible swiftness, with some finishing a full revolution in under 2 decades. This dynamic core, a site of both genesis and annihilation, functions as the galaxy's stabilizing point. Were it absent, the Milky Way's nucleus would disintegrate. The entirety of the galaxy rotates around this central point. This occurs once every 230 million years, a pace so gradual that the Sun has finished merely one orbit since the era of dinosaurs. Each complete rotation reconfigures the locations of billions of stars, yet from our perspective, the galaxy appears motionless. Notwithstanding its vast expanse, the Milky Way possesses an astonishingly slender profile. Should it be scaled down to the dimensions of a dinner plate, its depth would be less than that of a single sheet of paper. Contained within that delicate disk are an estimated 100 to 400 billion stars, and potentially more planets than there are grains of sand across our entire Earth. Nevertheless, the galaxy predominantly consists of vacant space. Imagine the Sun as a basketball. The closest star would then be another basketball, situated more than 2,000 miles distant. The intervening void would hold virtually nothing, an almost absolute vacuum with merely a few hydrogen atoms floating within each cubic meter. This vast emptiness truly characterizes the galaxy's essence. What photographs depict as a dense ocean of light is in reality predominantly darkness. Even within the most concentrated areas of the Milky Way, the typical separation between stars far exceeds anything the human mind can readily grasp. This profound isolation clarifies why interstellar journeys continue to be the supreme hurdle. The vastness of these distances is simply overwhelming. Despite this, the Milky Way is anything but motionless. It represents a dynamic entity sculpted by the forces of gravity and the passage of time. Frigid gaseous clouds condense, giving rise to nascent stars. Enormous suns detonate in supernova events, dispersing carbon, oxygen, and iron throughout the cosmos. These very elements then serve as the foundational components for planets, and ultimately, of life itself. Our Sun is a second-generation star, having emerged from the remnants of previous stellar bodies. The calcium found in our skeletal structure, the iron coursing through our veins, and the oxygen we inhale were all synthesized within primordial stellar furnaces. Each living organism represents a continuation of the galaxy's ongoing chemical narrative. Matter is perpetually recycled, reconfigured, and brought to light. The spiral arms of the galaxy aren't static formations. Instead, they're density waves traversing the disk. These patterns compact gas as they move, triggering new star formation. While the Perseus and Sagittarius arms constitute two primary spirals, our solar system resides in a more serene passage situated between them. Within these tranquil zones, supernovae occur infrequently and radiation levels are minimal, circumstances potentially enabling life on Earth to develop without interruption. If our location were nearer to the galactic center, where stars are densely packed and black holes consume matter, our planet's nights would be perpetually illuminated, yet life as we understand it might not have endured. Located approximately 26,000 light-years distant at the core, Sagittarius A represents one of the most extreme settings within the observable cosmos. Its gravitational pull distorts both space-time. A timepiece positioned close to its boundary would operate at a slower rate compared to one on Earth. Scientists have witnessed stars accelerating around it at speeds reaching thousands of kilometers per second, serving as real-world demonstrations of Einstein's theory of relativity. For anyone situated near that central region, the heavens would remain perpetually bright. Stars would occupy every visual perspective, and radiation would emanate from all sides. Conversely, our location on the periphery offers serenity, a cosmic viewpoint characterized by exceptional steadiness. Within a galaxy forged through tumultuous processes, from our vantage point inside the galactic disk, we lack a direct view of our home's complete architecture. This situation is akin to residing in an expansive metropolis, yet only perceiving the closest streetlights through a dense mist. Scientists assemble its configuration by employing radio, infrared, and microwave observations. By charting the movement of stars to reconstruct its morphology, these investigations uncover an unforeseen discovery. The observable galaxy constitutes merely a fraction of its actual mass. Encircling the Milky Way is an immense dark matter halo, an unseen material that exceeds the combined mass of all stars, planets, and gas by almost a 5-to-1 ratio. This substance neither radiates nor takes in light, yet its gravitational force holds the galaxy cohesively. Absent this invisible halo, the stars located further out would disperse, incapable of maintaining their orbital paths. Dark matter serves as the unobserved scaffolding of the Milky Way, the foundational structure supporting its visible form. Despite possessing this concealed mass, totaling approximately 1 trillion times the Sun's mass, the Milky Way remains unremarkable when judged by universal benchmarks. Certain galaxies, termed dwarfs, encompass merely a few billion stars. In contrast, others, such as IC 1101, are colossal, extending across 500,000 light-years and containing hundreds of trillions of suns. Our galaxy is positioned comfortably between these two extremes, neither the most immense nor the most diminutive, but rather one among innumerable spirals floating within the cosmic expanse. Each star, visible to the unaided eye, is a component of this solitary galactic island. Even the most luminous celestial objects, such as Sirius or Vega, are constituents of the Milky Way's proximate vicinity. The indistinct streak extending across the nocturnal heavens represents our sideways perspective of the galactic disk, where billions of remote stars merge into a gentle, silvery luminescence. For an observer situated outside our galaxy, that whole band would diminish to a solitary dim glimmer amidst billions of others dispersed throughout the void. The illumination originating from those far-off stars is exceedingly old. The light particles reaching your vision this evening might have commenced their voyage prior to the emergence of Earth's initial cities, or even before humanity came into being. We perceive the Milky Way not in its current state, but solely as it appeared millennia ago. This serves as an indication that each sky illuminated by stars also functions as a portal through temporal dimensions. The Milky Way itself undergoes perpetual transformation. Its spiral arms contort, its lesser companion galaxies coalesce and dissipate, and its stars progressively migrate outwards across vast stretches of time. Currently, our galaxy is assimilating multiple satellite galaxies, among them the Sagittarius dwarf galaxy, drawing their stars into elongated ethereal currents that encircle the disk. This gradual phenomenon of galactic assimilation is the mechanism by which galaxies expand, by consuming adjacent systems and integrating their stellar components into novel configurations. Nevertheless, despite its immense might, the Milky Way appears delicate when contrasted with the universe encompassing it. It drifts within an expansive cosmic expanse, encircled by other galaxies too remote for their gravitational forces to exert a binding influence. Each new finding concerning it, its dimensions, its bulk, its movement, culminates in an identical understanding. The scale is relative. Our cosmic dwelling, the Milky Way, is incomprehensibly vast, yet it's merely a tiny part of the universe's overall plan. A structure even larger exists beyond its luminous spiral arms. This structure reveals the true insignificance of a single galaxy. We commonly envision our galaxy as a sparkling metropolis of stars, with every dark area concealing an additional sun. However, the actual situation is much more isolated. The expanse between individual stars is so immense that light, traveling at 300,000 kilometers per second, requires several years to traverse it. Proxima Centauri, our closest star, is situated slightly more than 4 light-years distant, approximately 40 trillion kilometers. To illustrate, if the Sun were a marble on the ground, Proxima would be a second marble positioned almost 1,000 kilometers away. In the space separating them, there's virtually nothing, just a handful of solitary atoms floating through an abyss of darkness that surpasses imagination. This immense void characterizes the Milky Way. Each star, planet, and comet exists as an isolated entity within a sea of space. The distances are astonishing, even within our own solar system. Voyager 1, the most distant spacecraft ever constructed, travels through space at 17 kilometers per second, a speed sufficient to orbit Earth in just 7 minutes. Nevertheless, it would require 75,000 years to arrive at the closest star. This sole piece of information demonstrates the immense scale of even our modest galactic region. While not absolute nothingness, space in the interstellar medium approaches it. On average, a single cubic meter of space holds merely 1 hydrogen atom. In contrast, the air we inhale contains approximately 10 to the 25th power molecules within an identical volume. In comparison, the most pristine vacuum achievable on Earth would appear incredibly dense. Still, this tenuous haze of gas and dust serves as the fundamental substance for forthcoming stars. Over countless millennia, gravitational forces coalesce it into enormous clouds. These locations function as molecular nurseries where hydrogen cools, condenses, and ultimately ignites. The apparent void, as it happens, is not truly empty. Rather, it represents potential, poised to transform into light. Within certain areas, these clouds radiate as nebulae, forming vast, vibrant formations such as the Orion Nebula or the Eagle Nebula. Inside these, nascent stars sculpt voids in the gas using their radiation and stellar winds, creating enormous pillars and arches of luminous material. However, such locations are uncommon treasures. The Milky Way largely consists of darkness, interrupted by fleeting, dazzling bursts of creation. In between these, the genuine interstellar chasm exists, a domain just a few degrees above absolute zero, where light may journey for years prior to encountering another particle. The distances encountered here challenge conventional understanding. The typical separation between stars measures approximately 5 light-years, with each light-year equating to almost 10 trillion kilometers. Light requires 8 minutes to journey from the Sun to Earth, yet it needs 30 million minutes to arrive at the subsequent star. Envision traversing a field that extends from the dimensions of a local area to the expanse of entire continents. Such is the magnitude we encounter in the spaces between stars. Even the galactic spiral arms, which appear so substantial in images, are predominantly empty space. Compact star clusters, such as the Pleiades or the Hyades, comprise thousands of stars densely clustered, yet they represent tiny havens within a cosmic desert spanning thousands of light-years. Someone traversing these vast distances could spend whole lifetimes without ever nearing another star. Astronomical experts characterize this equilibrium as a cosmic ecosystem. Stars originate in clusters, then gradually separate and disperse throughout the galactic disk. The immense distances separating them serve as a protective barrier, hindering frequent impacts even while the galaxy undergoes its dynamic processes and development. Radiation from long-past supernovae and high-energy cosmic rays flows through these empty regions at speeds approaching that of light. Each second, countless unseen particles, remnants of deceased stars, traverse your form, bearing the intense energy of their tumultuous genesis throughout our galaxy. This void presents both a challenge and an insight for humankind. Our vessels become powerless well before traversing this expanse, and our swiftest radio transmissions dissipate into static after merely a few light years. Even traveling at light speed, a basic greeting directed at the closest star would require 4 years for delivery and an additional 4 for its reply. However, this identical void, which divides celestial bodies, simultaneously provides lucidity. It functions as an untouched laboratory where light and gravitational forces operate without interference. Through examining subtle aberrations in stellar light, scientists are able to determine the makeup and warmth of distant gas clouds, many light years distant. This emptiness transforms into a type of optical device, a tool through which the cosmos unveils its nature. Our planetary system navigates this environment within the heliosphere, an immense sphere shaped by the solar wind, which is an outflow of energized particles emanating from the sun. The heliopause marks its boundary, a point where the sun's dominion gives way to the force of the space between stars. During the year 2012, Voyager 1 traversed this boundary. Its sensors registered a significant increase in cosmic rays and a slight alteration in magnetic fields. This was the initial undeniable indication that an artifact of human origin had penetrated the region beyond our star system. To this day, it continues its silent yet consistent outward journey. It bears with it the subtle pulse of Earth, a gilded testament to our existence within a galaxy that might remain forever unaware. Despite appearing almost stationary from our perspective, the material between stars evolves across vast cosmic timescales. Nebulae move, powerful waves propagate from stellar explosions, and stars gradually orbit the core of the galaxy. Within several million years, our planetary system will transition into a different area, potentially more concentrated or less dense. This subtly modifies the equilibrium of cosmic radiation and solar illumination that arrives at Earth over human generations. Even though the heavens seem static, star patterns will retain their configurations for many tens of millennia. Their imperceptible movement is much too slow for human vision to detect. Grasping the nature of the space between those remote luminaries transforms our perception of them. Every star is more than just distant. It is divided by an abyss so immense that even our minds struggle to comprehend it. The void separating stars imparts structure to the galaxy, with the absence of matter delineating the luminous regions. As we venture further into the cosmos, this arrangement recurs. Aggregations of stars yield to larger interspaces, and galaxies to even more expansive vacuums. The further our observation extends, the more the cosmos discloses its fundamental architecture. A universe predominantly composed of emptiness, where infrequent bursts of substance and force delineate the delicate framework of being itself. Upon gazing past the Milky Way, we discover that even our immense galaxy has companions. It belongs to a modest galactic family, a gravitationally linked assembly journeying collectively through the void. Scientists refer to this as the local group, an aggregation of approximately 50 galaxies dispersed over an area spanning around 10 million light-years. The majority of these galaxies are diminutive dwarfs, dim specks of illumination discernible solely with potent telescopes. They revolve around the two principal behemoths of our group, the Milky Way and the Andromeda Galaxy, akin to small vessels navigating around a duo of grand ships. These two celestial bodies exert primary control over the area. Their gravitational pull guides the lesser galaxies into expansive elliptical paths. An immense expanse of intergalactic void stretches between them, so enormous that light itself requires over 2 million years to traverse it. Andromeda, identified also as Messier 31, stands as our closest substantial galactic neighbor and closely resembles our own. It presents as a barred spiral, roughly double the Milky Way's diameter, potentially housing 1 trillion stars. From our planet, it manifests as a dim, indistinct area within the Andromeda constellation, representing the furthest entity observable without optical aid. Observing it means witnessing photons that commence their voyage prior to the emergence of humanity as a distinct species. Notwithstanding that immense separation, Andromeda and the Milky Way are destined for a cosmic impact. Both galactic systems are approaching one another at approximately 110 kilometers per second. Approximately 4 to 5 billion years from now, their paths will converge. This occurrence will not be akin to a forceful impact of solid bodies, as galaxies primarily consist of vast empty regions. Their respective stars will largely traverse one another without interaction, due to the immense distances making direct impacts exceedingly uncommon. Rather, gravitational forces will deform and elongate both galaxies into tidal currents, propelling stars into extended luminous trails prior to their ultimate fusion into a solitary, more massive system. This forthcoming galaxy, occasionally referred to as Milkomeda, is expected to be a colossal elliptical, a golden, globe-shaped aggregation of stars lacking discernible spiral arms. The fusion process will initiate fresh bursts of star creation as gaseous clouds impact and condense, momentarily rekindling the universe's stellar forge. Our sun, approaching its final stages of existence by that time, might still revolve within this emergent formation, traversing a firmament abundant with innumerable nascent stars and luminous tidal curves spanning the cosmos. Prior to that magnificent rendezvous, our galaxy maintains its engagement with lesser companions already within its orbital path. The most notable among these are the Large and Small Magellanic Clouds, a pair of irregular dwarf galaxies observable from the southern hemisphere as dim, separate luminous areas. These are held by the Milky Way's gravity, gradually being pulled nearer. Tidal forces rip hydrogen gas streams from them, creating a link between these galaxies and our own. Eventually, they will also be absorbed, with their stars and gas integrated into the Milky Way's external disk. Accompanying us are scores of even tinier galaxies, including faint dwarf systems like Sagittarius, Fornacis, and Draco. A significant number of these are already undergoing disruption. Their remaining parts manifest as elongated stellar streams winding through the Milky Way's halo. Such stellar currents serve as indicators of galactic development, demonstrating that galaxies expand through the assimilation of others. The Milky Way's peripheral areas act as a repository for these occurrences. Every stellar arc represents a fossilized account of a previous impact. Gravitational force acts as the designer of this celestial vicinity. Each galaxy within the local group experiences its attraction, charting unseen trajectories within the collective gravitational field. However, gravity simultaneously functions as the creator of separation. Outside our local group resides the local void, a vast, nearly vacant expanse where galaxies are scarce. The boundary of the local group delineates the extent of our collective gravitational influence. Past this point, the universe's general expansion surpasses our reciprocal pull. At that magnitude, all other entities are moving away from us, not due to their motion through space, but because space itself is undergoing expansion. Within our group, nevertheless, the narrative is one of gradual coming together. Across eons, gravitational forces will persist in pulling its constituents closer. The dwarf galaxies will coalesce into the larger ones, and ultimately Andromeda and the Milky Way will combine at the group's core. Surrounding them, the leftover galaxies will revolve akin to fragments orbiting a colossal radiant nucleus. The local group will transform into a solitary, more expansive galaxy floating in the void. It will be a luminous isle set apart by the ever-enlarging cosmos. While this phenomenon might appear destructive, it is inherently natural and ongoing. Each substantial galaxy observable presently represents the outcome of innumerable fusions. The intricate spirals we appreciate are merely transient configurations within an extensive evolutionary timeline. Galaxies develop, mature, and change akin to stars, not over years or centuries, but across eras encompassing billions of years. Our comprehension of this cosmic vicinity has significantly broadened over the past 100 years. Astronomers of earlier times once believed the Milky Way contained the entirety of the universe. It was not until the 1920s that Edwin Hubble demonstrated Andromeda to be an entirely distinct galaxy, rather than a nebula within our own. This provided the initial proof that the universe stretches far beyond our galaxy. That finding altered everything. It showed that the Milky Way, previously thought to encompass all existence, is just one among innumerable galaxies dispersed across boundless darkness. Viewed from that angle, the local group constitutes not an expansive territory, but a minuscule segment of the discernible cosmos. Further out are superclusters, colossal collections of thousands of galaxies, and past those, the cosmic web, where material strands extend for hundreds of millions of light years. However, those enormous formations will be discussed in subsequent sections. Within our immediate vicinity, we observe the direct influences molding our destiny, the gradual interplay of galaxies, the continuous transformation of shapes, and gravity's silent endurance over immeasurable periods. Should we be able to peer 5 billion years into the future, the nocturnal heavens would scarcely resemble what we currently perceive. Andromeda would expand in size with every passing century. Initially a dim blur, then a luminous curve spanning the firmament. Once the galaxies ultimately coalesce, any surviving future onlookers would witness immense rivers of stars extending from one edge of the sky to the other. The Milky Way would cease to exist as an independent body. Its distinctiveness, much like our own, would blend into a novel form. Nevertheless, the underlying physics persists unchanged, even in that distant epoch. Gravitational forces will maintain their deliberate orchestration, molding light and substance into fresh configurations. Galaxies will persist in their formation, fusion, and eventual dimming, with the local group now a unified grand system. It will journey solitary into the ever-expanding emptiness, a luminous remnant from the universe's nascent era. Outside the local group, gravity arranges the cosmos into formations so vast they resist immediate understanding. Our modest galactic cluster navigates within a considerably vaster domain known as the Virgo supercluster. This extensive region spans over 100 million light-years. Inside it reside thousands of galaxies, held together not by discernible connections, but by gravity's unseen attraction, weaving through the cosmos. At its core lies the Virgo cluster, a massive assembly exceeding 1,300 galaxies. While some are spiral formations akin to the Milky Way, the majority are colossal ellipticals, sleek, ovoid groupings of ancient stars, emitting a subtle golden luminescence. These galaxies circulate around each other at velocities up to 1,000 kilometers per second. They traverse through superheated gas that occupies the cluster's inner volume. This gas, with temperatures reaching tens of millions of degrees, radiates X-rays, uncovering a network of plasma extending among galaxies. Nevertheless, based solely on observable mass, the Virgo cluster ought not to be present. The stars and gaseous matter we are able to perceive contribute merely a portion of the gravitational force necessary to maintain the cluster's cohesion. Lacking an extra invisible element, the galaxies would have dispersed ages ago. This unseen framework is dark matter, an enigmatic type of mass that neither emits nor absorbs radiation, yet exerts gravitational pull. Studies indicate that dark matter's mass is approximately 5 times greater than that of ordinary matter. It creates immense halos surrounding each galaxy and links them within extensive filaments that traverse the space between galaxies. Thus, dark matter functions as the universe's concealed structure, where it gathers gravitational force, attracts gas, which subsequently cools and coalesces into stars and galaxies. Across eons, this unseen design has molded the observable cosmos, transforming arbitrary disorder into complex arrangements. While direct observation is impossible, its existence can be inferred via gravitational lensing, the phenomenon where colossal bodies curve and warp light originating from distant galaxies. Monitoring these deformations charts the undetectable mass, exposing dark matter networks extending between clusters, resembling threads of celestial silk. Our local group is situated on one such thread, a minor offshoot of an enormous web reaching well past the Virgo cluster. During 2014, astronomers meticulously mapped this area with unparalleled precision and ascertained that the Virgo supercluster constitutes merely a segment of an even grander formation. Designated the Laniakea supercluster, signifying immense heaven in Hawaiian, this supercluster covers approximately 500 million light-years, containing over 100,000 galaxies, all converging inward towards a gravitational nexus termed the Great Attractor. The Great Attractor is not an individual entity, but rather an area of profound gravitational pull situated approximately 150 million light-years distant, close to the Norma constellation. This phenomenon influences the movement of galaxies across vast stretches, our own Milky Way, Andromeda, and thousands of neighboring systems included. All are being drawn towards it at roughly 600 kilometers per second, even though the universe is expanding generally. Gravity in our local area generates streams of movement that converge upon the most concentrated regions. Our entire cosmic vicinity is ensnared within this flow, gradually descending towards the invisible core at Laniakea's center. When astronomers chart these movements of galaxies, the outcome is akin to a 3D oceanic current diagram, with galaxies behaving like particles within an immense, unseen current. Supercluster boundaries are not rigid barriers, but rather areas of transition where the movement's course alters, much like watersheds delineating rivers on a planet's surface. Laniakea itself is linked with other colossal formations, constituting a segment of an even grander aggregation, occasionally referred to as the Pisces-Cetus supercluster complex. This interconnected system of superclusters stretches over 1 billion light-years. If we observe from a sufficient distance, the universe starts to display a surprising arrangement. Galaxies are not haphazardly dispersed through space. Instead, they constitute an immense interwoven cosmic network. Extended galactic filaments span hundreds of millions of light-years, converging at concentrated points, which give rise to galaxy clusters. Immense cosmic voids are situated between these filaments. These areas are so devoid of matter that entire superclusters might be contained within them without meeting any galaxy. Computational models depicting the universe's development, like the ones derived from the Millennium Simulation or the Illustris Project, reproduce this cosmic network with impressive precision. Soon after the Big Bang, minor variations in matter density expanded due to gravitational pull. Initially, dark matter aggregated, creating unseen halos. Subsequently, ordinary matter cooled and condensed along these very filaments. Across eons, this mechanism gave rise to our present-day cosmos. An immense web of luminous galaxies delineates the contours of invisible material. Every filament functions as a celestial thoroughfare, guiding gas, stellar bodies, and galaxies towards the most concentrated junctions. Such junctions evolve into galactic clusters, which are the cosmos's major metropolises. Conversely, the intervening voids resemble barren expanses, frigid, dim, and almost entirely vacant. The most expansive identified voids, for instance, the Bode's void, extend across hundreds of millions of light-years and house merely a few dozen galaxies in a space expected to accommodate thousands. Within these regions, the nocturnal heavens would seem nearly vacant, even when viewed with the most advanced telescopes. Gravity is the force that binds this immense network, yet what propels its separation is an even greater enigma, namely, dark energy. This invisible power, uncovered in the latter part of the 1990s, functions as a form of cosmic impetus which hastens the cosmos's enlargement. At dimensions less than superclusters, gravitational force prevails, uniting galaxies and clusters. However, over greater expanses, dark energy triumphs, propelling the cosmic network outwards, causing its filaments to attenuate over time. The equilibrium between these dual forces, gravity and dark energy, establishes the cosmos's architecture. The network is formed by gravity, while dark energy disassembles it. Across countless millennia, galactic clusters and superclusters will grow increasingly solitary due to the space separating them, expanding at a rate exceeding the speed of light. Ultimately, just those galaxies held together by localized gravitational forces, such as our future combined system of the Milky Way and Andromeda, shall continue to be observable. The remaining ones will recede past our cosmic boundary, their illumination perpetually beyond our grasp. At this current juncture, however, humanity exists during a unique period in cosmic evolution. The network is completely developed yet remains discernible, allowing us to follow its threads, gauge their movements, and chart the fundamental structure of reality. Should astronomers direct the Hubble Space Telescope towards a seemingly vacant region of the heavens and allow it to gather light for an extended duration, it uncovers thousands of galaxies in an area where no visual observation was possible. Each individual pixel transforms into a portal to profound antiquity. Every galaxy represents a stellar metropolis emitting light over eons. When observed collectively, these galaxies delineate the very scaffolding of the cosmos. The cosmic network transcends mere structure. It embodies history rendered perceptible. Each galactic cluster signifies an area where material had previously aggregated with slightly greater density than the norm. Each void signifies a region where matter was marginally less plentiful. The arrangement we observe now represents the solidified remnant of quantum variations that arose mere moments after the Big Bang. The Milky Way galaxy, our Sun, and even Earth itself belong to this configuration, acting as localized undulations within a universal web spanning all existence. The very atoms comprising us were formed by this framework. Hydrogen originated during the Big Bang, while more massive elements were created within stars, with both types dispersed along dark matter strands that directed their movement. We don't merely exist within the cosmos, we are manifestations of its grand architectural design. Should we be able to exit the universe and observe it from an unattainable viewpoint, a fragile network of light would become visible. Galaxies would appear threaded along immense filaments, emitting a gentle radiance amidst perpetual gloom. It would resemble less a haphazard distribution of points and more a vibrant entity, akin to a network of veins or neurons linking all aspects of being. The identical principles that control the most minuscule particles of substance also dictate this magnificent structure. Spanning from quantum variations to immense galactic superclusters, the cosmos constructs intricacy via recurrence, balance, and duration. And within that intricate network, our galaxy, despite its immense size, is merely a single shining point. It stands as a solitary junction amidst countless others. Its radiance, its past, its interactions, and its existence are all components of a framework vastly exceeding anything the human intellect developed to grasp. Nevertheless, we are somehow capable of charting it, detailing it, and comprehending its genesis. From the expansive filaments of the cosmic network to the void separating its strands, every observable entity, each planet, star, and galaxy, follows the identical, unseen framework. And as our gaze extends into that colossal formation, a singular understanding emerges. The Milky Way, despite its splendor and movement, constitutes merely a strand within an unending cosmic artwork. It represents one solitary shining fiber integrated into the boundless material of the cosmos. Should the Milky Way be considered a metropolis and the local group a region, then the cosmic web functions as the continent, with the discernible boundary of all existence lying beyond it. The universe we can observe stands as the most expansive formation we can discuss with significance. This represents the complete expanse of space-time from which light has had sufficient duration to arrive at our location since the universe's inception. This demarcation is situated approximately 46.5 billion light-years distant. From every vantage point, this figure appears contradictory. The cosmos is merely 13.8 billion years old. So how is it possible for us to perceive objects beyond 13.8 billion light-years? The solution resides in the very expansion of space. While light journeys towards us, the cosmos expands, propelling remote galaxies further away even as their illumination persists. Its voyage. What we perceive presently is not the current location of those galaxies, but rather their position billions of years in the past. Each direction we gaze in constitutes a glimpse into the past. The illumination from an Andromeda star reveals that galaxy to us as it appeared 2.5 million years prior. A quasar, situated 10 billion light-years distant, unveils the cosmos as it existed when galaxies were merely starting to take shape. And at the furthest extent, the subtle microwave radiance enveloping us originates from an era preceding the existence of any stars or galaxies whatsoever. This luminescence is known as the cosmic microwave background, or CMB, which is the residual radiance of the Big Bang itself. It represents the most ancient light we are able to detect, emitted when the cosmos had reached an age of just 380,000 years. Prior to that instant, the universe comprised a scorching, impenetrable plasma of elementary particles and energy. Light was unable to traverse unimpeded. It underwent continuous dispersion by electrons. However, as the cosmos enlarged and lost heat, atoms materialized, the obscuring haze dissipated, and the initial photons commenced their journey through space. These are the identical photons we continue to observe presently, elongated by universal expansion into subtle microwave radiation. The CMB saturates the celestial sphere uniformly, presenting as an almost consistent field of radiation, precisely 2.7 degrees above absolute zero. Upon detailed mapping by satellites such as COBE, WMAP, and Planck, tiny discrepancies were discovered, temperature shifts as minute as 1 part in 100,000. Every star, planet, and living entity ultimately owes its existence to those subtle ripples in the Big Bang's afterglow. These minute variations signify the foundational elements of structure, slightly more concentrated areas that gravity would subsequently magnify into galaxies, clusters, and the entire cosmic web. The entire span of cosmic history unfolds between the cosmic microwave background and our present era. Following the formation of the initial atoms, the cosmos transitioned into an era termed the Cosmic Dark Ages. No stellar bodies had yet ignited, only neutral hydrogen pervaded the expanding cosmos. For countless millions of years, the universe remained dim and hushed, its energy contained within unseen matter and cooling radiation. Subsequently, gravity began its influence. Minute regions of higher density expanded, pulling gaseous material inward until the initial stars ignited. These were luminous, ephemeral, colossal bodies that inundated the cosmos with light and ultraviolet radiation. Their emergence marked the conclusion of the Dark Ages and ushered in a new epoch, cosmic reionization. As light once more pervaded the cosmos, the initial galaxies began to form, congregating into groupings along the dark matter filaments. By the time the universe reached an age of 1 billion years, the fundamental structure observable today, comprising stars, galaxies, and immense voids, had already been established. From that point forward, the narrative shifted to one of expansion and evolution. Galaxies coalesced, expanded, and developed. Stars completed their life cycles. More massive elements dispersed throughout interstellar space, paving the way for planets and ultimately life. Nevertheless, the universe itself persisted in its expansion. Light emanating from remote galaxies reddened, undergoing a wavelength shift, elongated due to cosmic expansion until it transitioned from the visible spectrum to infrared. Subsequently, it moved to microwave frequencies and ultimately became undetectable. As our observational range extends, objects appear increasingly redshifted and ancient. This continues until we reach a distance where the light has been elongated to a near infinite degree. That constitutes the cosmic horizon, the boundary of our observable cosmos. Beyond this horizon, a significantly larger universe may exist, possibly infinitely vaster, yet it remains forever inaccessible to us. The expansion of space is exceedingly swift at such vast distances, meaning even light is unable to traverse the expanse. We are capable of calculating and envisioning its contents, but we will never directly perceive it. The boundary of the observable universe does not represent a physical barrier. Rather, it is a horizon delineated by temporal and kinetic factors. Within this horizon, the magnitude of existence is astonishing. The observable universe encompasses approximately 2 trillion galaxies, each housing hundreds of billions of stellar bodies. In total, there exists a greater number of stars than all grains of sand on every beach across Earth, and each one could potentially harbor its own planetary systems, its own narratives, and perhaps even its own forms of life. Nevertheless, these innumerable stars constitute under 0.1% of the entirety of existence. The remainder consists of dark matter and dark energy, invisible but prevailing. Were we able to journey outward at light speed, we would traverse both temporal and spatial dimensions. We would first pass the Milky Way's adjacent galaxies, then the Virgo cluster, followed by the filaments of Laniakea, all receding into the distant past after billions of years. The universe would appear progressively younger before our eyes. Galaxies would seem more compact and bluer, their light blue shifted due to our relative motion. Ultimately, we would arrive at the era when the initial galaxies were in their nascent stages. The universe was merely several hundred million years of age. Subsequently, as we continued our journey even deeper, stars would disappear completely. They would be succeeded by the gentle, consistent luminescence of the CMB, the ultimate observable remnant of antiquity. Beyond that point, there is no further illumination, only the quantum fog of the very Genesis. That Genesis, the Big Bang, does not represent an explosion within space. Rather, it signifies the expansion of space itself. It occurred simultaneously across all locations, with each point within the cosmos expanding away from every other. The universe lacks both a central point and boundaries. It appears uniform in every direction, either boundless or almost so. The phrase Big Bang refers not to an explosive instant, but to the evolution of being from a scorching, compact condition into the immense configuration we observe presently. Presently, the cosmos persists in its expansion, and this growth is speeding up. Far-off galaxies are moving away at increasingly rapid rates, propelled by the enigmatic power known as dark energy. Many billions of years hence, in the distant future, the majority of galaxies will have passed beyond the limits of what we can observe. The nocturnal heavens will become more vacant, the universal network will dissipate, and any future civilizations might completely lose all proof of a vaster cosmos. Consequently, we inhabit a singularly fortunate period, a time when the universe has matured sufficiently to develop its framework, yet remains youthful enough for us to perceive its genesis. Our lineage can be followed through almost 14 billion years of cosmic events, from stellar-produced atoms to the initial light emitted at creation's dawn. Each observation, every single photon, conveys information from that bygone era. Gazing at the nocturnal firmament reveals not a spatial chart, but rather a chronological sequence. Every luminous point represents a recollection, and each galaxy serves as an account of a prior cosmic state. The universe we perceive is simultaneously ancient and dynamic, perpetually enlarging, yet forever connected to its genesis. Within this vast observable realm, among 2 trillion galaxies and countless stellar bodies, lies a modest spiral galaxy. Situated at the periphery of a typical supercluster, hosting a star and a few planets, resides a species that has started to comprehend the significance of it all. Beyond that visible boundary at the very edge of the discernible cosmos, light diminishes into nothingness. Beyond that unseen frontier, there exists no data, no light particles, no transmissions, merely formulas, theoretical constructs, and conjecture. Nevertheless, the principles of physics enable us to theoretically glimpse what might exist past that unseen limit. The initial fundamental fact is straightforward. The universe we can observe does not encompass the whole universe. This is simply the area from which light has managed to travel to us over a span of 13.8 billion years. However, space itself has been undergoing expansion during that entire duration. Areas beyond our perception persist, evolving continuously, populated by galaxies whose illumination has not reached us and never will. Experts in astronomy calculate that the complete universe might be at least 250 times vaster than its observable segment and potentially boundless. The human intellect struggles to readily grasp the notion of infinity. Within a boundless cosmos, each configuration, every organization of substance is bound to recur at some inconceivably distant location. It is conceivable that an identical region to our own exists. A different Earth, a distinct Milky Way, another version of you, living within a marginally altered trajectory of universal history. These are not mere imaginings, but rather outcomes stemming from fundamental geometry and physics. Should space genuinely be boundless and consistently permeated with matter, the concept of beyond also prompts a more profound inquiry. Did the cosmos possess a spatial boundary or an initial point? Based on Einstein's theory of general relativity, the response is negative. The universe lacks a spatial boundary. It is curved solely in terms of time, possessing a finite volume yet being limitless, akin to the exterior of a sphere. Were one to journey in a direct path for a sufficient duration, one could ultimately arrive back at the origin, not due to space abruptly circling, but rather because it curves. The cosmos encompasses itself on more confined dimensions. This scenario becomes even more intricate due to quantum mechanics. In the initial instance of being, under a trillionth of a second following the Big Bang, the cosmos is believed to have experienced a phase of universal inflation, characterized by an abrupt, rapid growth propelled by an unidentified energy field. During that fleeting moment, space might have expanded at a speed exceeding that of light, thereby homogenizing the universe and extending quantum variations into the foundational elements of galaxies. However, if inflation did occur, it may not have ceased simultaneously across all areas. In certain locales, the phenomenon could still be ongoing. This brings forth one of the most captivating hypotheses in cosmology, the concept of the multiverse. According to this perspective, our universe represents merely a single bubble within an immense, perpetual foam of space-time, where fresh universes continuously emerge while older ones enlarge. Every such bubble could possess distinct physical principles, fundamental constants, or spatial dimensions, an endless diversity stemming from identical foundational physics. While direct empirical verification of this notion is beyond us, mathematical reasoning suggests its likelihood. Magnified by inflation, quantum fluctuations might give rise to entirely new spatial regions. Certain physicists liken this to an expanding foam, with each bubble representing a distinct universe, each possessing its own unique reality. Within one such universe, gravity could be more potent. In another, atoms might not even manifest. The majority of these cosmic realms would likely be barren, devoid of life, and shrouded in darkness. However, probabilistic principles indicate that a few, similar to our own, might sustain intricate complexity, chemical processes, and sentient awareness. Should this prove accurate, the concept of the multiverse would fundamentally redefine our understanding of scale. Our observable universe would then become merely a single volume within an infinite cosmic archive. Every volume is self-sufficient, with its narrative dictated by its unique physical laws. Considering this perspective, even the Milky Way's 100 billion stars appear as a mere localized feature within an unbounded structure. Yet, even more profound limitations might exist. The Planck scale represents a threshold, past which our comprehension of space-time ceases to function. At dimensions smaller than this, gravity and quantum mechanics interact in manners that no existing theory can adequately explain. Reality's fundamental structure grows ambiguous, teeming with such powerful fluctuations that space and time might shed their conventional definitions. Advancing past this boundary would necessitate a unified theory, termed quantum gravity by physicists, capable of harmonizing Einstein's concept of curved spacetime. In conjunction with the probabilistic domain of quantum fields, the quest for such a theory has generated novel concepts. These include string theory, which posits that all particles are minute vibrating strings inhabiting up to 11 dimensions, and loop quantum gravity, which portrays space as an interconnected web of distinct loops, akin to a finely woven textile of finite strands. While these remain unproven, they suggest the universe could be simultaneously continuous and granular, boundless in scope, yet fundamentally quantized. Even beyond this, a more profound philosophical question emerges. What is the reason for existence itself? While science can map the progression from quantum fluctuations to the formation of stars and galaxies, the ultimate cause of existence itself falls outside the purview of physics. Certain theories put forth the idea that universes spontaneously emerge from probabilistic laws, essentially that existence is the inherent condition of mathematics. Conversely, some contend that posing Y implies a necessary cause where none exists. The universe simply is. What we can assert with certainty is that the cosmos functions according to coherent, discernible principles. These principles govern everything from a moon's orbital path to the movement of whole galaxies. Furthermore, these principles have persisted unchanged throughout 13.8 billion years of cosmic evolution. This steadfastness enables us, diminutive beings on a minor planet, to comprehend phenomena taking place trillions of kilometers distant and eons in the past. Nevertheless, even the most accurate theories possess limitations. We are unable to perceive beyond the cosmic event horizon. We cannot investigate what preceded the dawn of time. We are incapable of extending our reach past the Planck scale. Each resolution reveals more profound inquiries, and perhaps this defines the very essence of knowledge. It's an unending vista that retreats further as we draw near. Should the observable universe be considered a luminous sphere, then the boundaries of scale delineate the obscurity beyond. However, that obscurity is not void, it is enigma. Ultimately, it is the genesis point of curiosity. As our understanding of the universe expands, we increasingly grasp how minuscule a portion of it we genuinely inhabit. Our galaxy stands as merely one amidst trillions, our perceptible domain just one among innumerable others, a fleeting instant, a brief spark in the vastness of cosmic time. Despite this ephemeral moment, we possess the capacity to gaze outward and reconstruct the narrative of creation itself. The constraints of scale serve as a reminder that while knowledge has frontiers, wonder is boundless. A new horizon always awaits beyond the last. Furthermore, the very endeavor of striving for it, of inquiring about what comes next, might represent the universe's most extraordinary achievement. Having journeyed across the cosmos, from the sun's orbital path to the most distant galaxies, from atomic structures to the grand cosmic web, we return to our point of origin. Upon a modest planet circling an ordinary star. From this vantage point, all we have observed manifests solely as light. Yet embedded within that light resides the entire chronicle of the universe. The magnitude we have discovered is astonishing. Our galaxy, the Milky Way, extends across 100,000 light-years. The local group encompasses 10 million. The Laniakea supercluster measures 500 million, and the perceptible cosmos stretches 46 billion light-years in all directions. However, the real significance of these vast distances isn't merely their physical extent. Rather, it lies in what they disclose, that all visible existence belongs to one unified, interconnected entity. Identical physical principles govern every stratum of existence. The gravitational pull anchoring you to Earth is the very same power that coalesces galaxies into clusters. The process of nuclear fusion energizing our sun is identical to the one that created the earliest stars. Your body's atoms consist of hydrogen originating from the Big Bang and more massive elements produced by primordial stars. These are fragments of cosmic history continuously recycled and reconfigured across eons. You are, in essence, a minuscule portion of the cosmos that has achieved self-awareness. From this perspective, being small ceases to imply insignificance. While the cosmos might be immeasurably immense, awareness, even when confined to a single delicate species on a tiny world, imbues that immensity with purpose. Importance isn't determined solely by size, rather it's understanding that defines it. As we gaze upon the universe, it is, in effect, the universe contemplating its own existence. This viewpoint alters our perception of all things. The vast expanses that previously appeared insurmountable now serve as chapters in one continuous narrative, the emergence, development, and evolution of matter into intricate forms, living organisms, and consciousness. Each galaxy, each planet, represents an additional stanza in that tale, a further endeavor by the cosmos to comprehend its own nature. Our own galaxy constitutes a single strand within a grand cosmic fabric, intricately spun from illumination and chronology. It is neither immense nor tiny, neither primordial nor nascent. It is merely a single instant within a continuous evolutionary process that commenced almost 14 billion years prior. Eventually, the Milky Way will coalesce with the Andromeda Galaxy. Stars will cease to exist, new ones will come into being, and ultimately, even those will diminish. The luminosity of our galaxy will wane until merely the subtle radiance of red dwarfs persists. Nevertheless, at some point within that immense temporal span, for a fleeting moment, it brought forth entities able to gaze skyward and ponder the reasons. Each instance we observe the nocturnal heavens, we are peering into bygone eras. Yet simultaneously, we are witnessing a mirror image of our own being. The constituent elements of our physical forms originated within those stars. Their destinies prefigure our own. The carbon enabling our cognition, the iron circulating in our bloodstream, and the calcium forming our skeletal structure. All of these were once radiant energy in the ultimate exhalation of a perishing star. The cosmos composes its narrative not through language, but through atomic particles. Grasping this concept does not diminish us. Instead, it integrates us into something truly vast. We are linked to the earliest galaxies, to the residual radiance of cosmic genesis, and to the distant future that will materialize long after humanity's disappearance. The identical configurations that formed nebulae and galactic clusters also structure the neural pathways within our minds. The identical mathematical principles dictating superclusters also dictate the helical structures of DNA. To comprehend this is to recognize that the cosmos is not merely a remote display, it is our dwelling. Despite its immense size, the Milky Way serves as our cosmic location, a transient position within an unending progression. Our galaxy will, at some future point, merge into a more massive one, and that larger entity will ultimately wander solitary within the ever-expanding void. However, the understanding we have acquired, our capacity to chart our beginnings from the initial light to the current era, will persist through the legacy of our creations and potentially in the reverberations of the transmissions we've dispatched into the cosmos. When discussing our smallness, we frequently perceive it as an indicator of influence or significance. Yet, within the grand cosmic framework, being diminutive is unavoidable. The truly remarkable aspect is that such a tiny entity can grasp the entirety of a universe spanning 93 billion light-years. Our intelligence is delicate, transient, and confined to specific areas. Its emergence was for the purpose of charting the entire universe's structure. This very process of comprehension constitutes a universal phenomenon. Galaxies will persist in their movement. The illumination will continue to dim. Eventually, perhaps only the documentation of those who once marveled at the stars will endure. Yet once wonder comes into existence, it cannot be reversed. It forms an integral part of the cosmos, just like gravity or light. This is a power that draws the intellect beyond its limits, towards the infinite. As our knowledge expands, its nature becomes increasingly evident. Our galaxy is diminutive, and our world is even more so. Nevertheless, through our consciousness, we achieve immensity. Each new finding, every observation, and every inquiry broadens the universe, not externally, but internally within our minds. The Milky Way represents only one among countless others, yet comprehending even a single one provides a glimpse into the essence of the entire collection. And to comprehend, even if only for a moment, that we are part of something significantly grander than our individual selves. Should you appreciate this video, please remember to give it a thumbs up and subscribe. This contributes immensely and assists in the channel's expansion.